Hey guys, my name is Lewis. Welcome back to our channel. We are Confido Cyber. We are celebrating this week a very big week for Microsoft as they release their quantum safe program updated strategy landing today. Later this week, we will be also doing a full debrief and breakdown of what that strategy is and likely covering the whole crypto quantum thing in a lot more detail. I am a leader within this space at Microsoft, and I played a key role in reviewing and writing that initial blog post. So I'd love to hear your thoughts. Anyway, here's some training that we did about 2 or 3 months ago on this whole topic. I hope you find this helpful in understanding what quantum is, why this is a problem, and what you need to be doing about it. So I wanted to talk firstly about the nature of quantum and where we are with that, and hopefully lead you on the process of understanding, well, why is quantum a threat for anything and what are the main use cases at the moment? And this is our roadmap on quantum. So you can see here April 24 all the way to this kind of mark here where we're breaking into the 50 logical qubits. And often what you'll see is lots of news articles talking about, so like there's a recent Chinese announcement, I've got a slide on that later, where they're talking about 500 qubits, which sounds like quite a big jump from 50. But then you realize that it's the logical qubits that actually matters. And actually you can have a lot of qubits, but actually qubits can be quite error prone, and there's a lot of things that go into making those qubits useful. So even though 50 sounds like a small number, that's 50 qubits that are optimized to achieve specific tasks. And actually, the more qubits that you have, the more almost parallel tasks you can do. And it's really when you start getting to the million qubit territory that you start to really have some useful practical applications. So the main two at the moment are chemistry-based solutions and cryptographic solutions, and there's various departments from like the UK government who are really excited about doing lots of cool things, solving all sorts of cool problems that they've never been able to solve before, harnessing quantum. There's lots of things that you can't do yet, and really the two main ones that are anywhere close to being done is cryptographic challenges as well as the chemistry based ones.
Can I ask a quick, sorry, interrupt. Quick question to level set. When you say qubits, I've heard qubits a lot, right? And it's the new, it is the quantum processor. Like, in a quick nutshell, like, how do we think about a qubit? Is that like when we were back in the 486 days, like we had one processor and two processors and four processors and eight processors? Is it like a processor, or what is just a quick high level 8 qubit?
Mm-hmm. Yeah, so a qubit is based on kind of hardware architecture, and that is currently massive. Like often, a small amount of qubits is like football fields worth of equipment, and a qubit has, unlike classical computing, you've got binary, and it can be either a 0 or 1. And my understanding is that a qubit can operate in kind of a multi. It can be both a 0 and a 1 at the same time, so it can kind of run in a slightly different way to how classical computers run, and it allows for parallel tasks. And initially, for the smaller types of tasks, classical computers generally run a lot quicker, but there's a certain kind of point that once you get enough compute, there's a crossover where quantum becomes a lot faster at running certain types of problems. So one of the questions in the chat was, what's the difference between a qubit and a logical qubit? My simple understanding is that you take a qubit and you kind of provide some additional error checking and some optimizations is the simple way I would think about it, to ensure that qubit can be practically used so you're kind of taking the raw resource and you're putting some controls around that, so that rather than it just doing anything, you're controlling the types of tasks that it can actually do. Is my kind of understanding.
So it sounds like it's really just like like what we would consider like the gates, right? The on-off bits.
Yeah.
Okay.
Yep.
Okay, thank you very
exactly.
much. That makes more sense. Thank you.
The size analogy is 50 qubits or 100 qubits would have taken a whole football field or soccer field, as you guys say in the US. The Morana 1 chip was a big breakthrough, mainly because you can hold it in the palm of your hand, and it's a technology that claims, and I think there's some prototypes out there that show that you can have 1 million qubits in the palm of your hand. So historic research and all of the other quantum providers are doing 50 qubits or 60 qubits, but they require a massive amount of space to do so. This is kind of the next leap, the same kind of leaps that we saw with classical computing. And I think it really brings the realm of possibility of having qubits reach that 1 million qubits, where it's effective qubits that can be trained and used for tasks. That's the biggest, and that's got big organizations really thinking about and considering, well, we actually need to take this seriously because the research is now there, and that's probably the biggest jump of all that's caused everyone to do that. And not only that, but there's lots of research recently coming out, such as one last month, where there's various algorithms being broken, and actually mathematically various encryption algorithms are on paper already being broken by concepts of quantum. So the groundwork is certainly there to show that actually even an AES 256 is very commonly used right now. So it's really causing the industry to think about that. And here's just an example of another announcement recently, where there's a lot of announcements that seem to come out of China that aren't always factually true, where they're claiming 500 qubits, and there's a lot of noise in the media claiming vast amounts of qubits. And the general guidance from the quantum team is to really look and see what sorts of qubits are they talking about. Are they talking about logical qubits, or are they just talking about raw qubits? So there's a lot of skepticism to be had here. IBM are probably one of the leaders in how they're talking about quantum computing, and this is one of their engineering roadmaps. And you can kind of see here that we're obviously in 2025, and 2029 is when they believe quantum is going to become more cost effective. That's the real crossover point between, because in security we have relied on security always being very expensive, so therefore that's a natural deterrent. However, that begins to shift about 2029, where the technology kicks in and we start to see actually more affordable use, and obviously politically motivated threat actors who aren't motivated by money. That's when I think they're going to start being using these types of technologies more. And even the UK police force, they'll occasionally use quantum computing to try and brute force criminal-based phones as like a last-ditch effort to try and break into various devices. So all of this stuff is starting to be explored in its use currently. And you can kind of see here there's quite a big jump between now and the next kind of 4 to 5 years in terms of various innovations across the board. IBM do an ingestion-based model. You can log into their website and spin up your own quantum computing, just like we do, and you can kind of pay for some time to then run your own queries against this kind of amount of compute that they give you. So this is becoming more and more accessible and more apparent, and no longer do you need the skill set of having to build your own quantum computing. Another trend we're seeing as well is the whole concept of harvest now and decrypt later. And if you're not familiar with that term, there's a lot of data harvesting that is happening anyway, and stockpiling that data, which is currently encrypted, and they're stockpiling that information so that that can be decrypted, where quantum computers are going to be more affordable in its usage. Now, you might think, well, that's not necessarily a problem for a lot of data, because, data in 5 years isn't going to be the same. However, that's a big privacy concern for data that isn't going to change, like social security numbers, maybe credit card information, passports, even addresses, names, etc. So there's a lot of privacy-based challenges that are already being presented right now that really affect how we're having to think about this problem due to these types of tactics that we're seeing. Now we've kind of covered the history of and some of the trends that we're seeing. I wanted to really go into the history of cryptography and to show you really how it works. And I think this is something that I'm actually surprised about how many people don't have this history, how cryptography works at a very, very simple level, just to help you understand the nature of the types of challenges of why this is a problem. So this is really a timeline from 1950, and that's when the NSA was set up to handle various types of problems like the cryptographic challenges, and the notion of cryptography and ciphering has been a thing since the Egyptians, or even before then, where various entities have attempted to try and conceal their messages, gain a tactical advantage over their enemies, or prevent. So this whole idea has been around for a long time, but this really has translated quite differently to an internet perspective when, weirdly enough, GCHQ in the UK invented RSA a few years before it was even. So they invented it confidentially, and they kept that in secret for a couple of years, and then famously RSA and key exchange. So Whitfield Diffie, Marty Hellman, who are the inventors of the Diffie-Hellman key exchange. So the concepts where you have two keys and you kind of exchange them to authenticate a user, and I'll explain what that is in a minute. So that's kind of them pictured there. Came along and invented that, and then we've kind of got work built on each of the academic people listed. So RSA, so Revest, Shamir, Edelman, who are listed here, invented the concept of the RSA algorithm. And there's kind of various other innovations as well in the history. So Pretty Good Privacy by Phil Zimmerman as well was invented in the 90s as well. So there's the concept of cryptography. It's weird to even think we didn't really have this prior to the 90s really, and even then the encryption used was pretty weak, if non-existent at all, and many people didn't even acknowledge the need for cryptography. With all of these things, so RSA was invented, so NIST have historically hosted competitions where they invite researchers to compete to select the problem of the day, and from that often there'll be a number of finalists selected who can develop the best algorithms, and that's been certainly the history, and that's what's happened recently where we had to think through, well, we need a quantum resistant algorithm. That's kind of obviously what's happened during this timeline. And at a very, very high level, and I'll kind of dive into this with a diagram in a second, you've got Alice and Bob. So Bob and Alice are a very they're standardized terms in how you talk about encryption, or kind of with Alice and Bob being two different individuals who want to communicate with each other. Typical names like Trent as like a certificate authority. So, and these are just kind of commonly adopted names when academics reference or talk about certain types of topics. So when you kind of see those names, it's kind of interesting to see. But I'll kind of walk you through what happens during a key exchange at a very basic level, and kind of hopefully that will help bring some clarity around that as well. So this is a mind map. I love mind maps, and I think it's a great way of showing a lot of information in one place. And you've got Alice and you've got Bob, and they both agree on their public numbers. So these are public numbers they share between each other. So they'll generate, in this case, 997, and which is a prime number, and a prime number is important, and I'll get to that in a minute. And they've also got a generated number, which is a smaller number, which is just a random number that's generated. And the real numbers that are generated are way, way, way bigger, but this is just for the example to show how this works. They then define a secret each. So Alice will generate a secret, which is, in this case, it's just number 23, and Bob will generate number 62, and you typically define this as I would say it as a variable. So like it's a variable being A or variable being B. So when you say B, it means 62, for example. And then there's a number of public values that that they generate, which is kind of that kind of establishes the connection. So there's a bunch of mathematics here happening, and that is sent to that's essentially it's used to create some encryption to send that encrypted message over to so Alice would send that to Bob and would also send the secret number to Bob in that encrypted message, and then they use those two numbers to decrypt that message, and the end result is they both end up with the same number, even though they use different kind of secrets all throughout the process. It's the way to think about it is it's a whole different process to reach the same number, and those numbers are kind of essentially they're compared, and that validates, oh yeah, I've got, you know, the right certificate here. So that's essentially how it kind of how it works. And the challenge here is if you know kind of, for example, this number, it's very, or letter, sorry, or value, it's very easy to work out this number here because you can kind of just do the sum. However, if you don't know this not this letter or value here, but you do know this value, it's very difficult to, because you're essentially reverse engineering that that value. So whilst it's quite quick to kind of encrypt something, when you know all of the information, it's very difficult to decrypt, especially when you're guessing that information, and that can be quite mathematically and computationally quite expensive, just because computers struggle to do it's called a mod of a prime number. So you're dividing a number within itself, and it's this essentially it's a really difficult for a computer to do, which is why it was used. And there's all sorts of other methods that computers use, like slower algorithms, or they introduce kind of a more randomization called SALT, or an initialization vector, to kind of make it essentially harder for you to kind of just guess that. But there's been some algorithms, quantum algorithms, that have come along to essentially mean that it's a lot easier to crack those types of numbers and types of problems. So the more compute you have, so typically something like this may have taken, you know, millions of years, but with the nature of how quantum computing is, it changes the whole dynamic of, with a classical computer, you have to have a 1 or a 0, whereas quantum is doing things differently. It can be a 1 and a 0 at the same time, and it's a lot quicker. And there's a lot more optimized hardware nowadays with the rise of AI. So there's hardware that's especially optimized for these types of tasks. So this is what's causing this type of an issue. And even though these numbers seem quite small, the bigger numbers, which are called large integers, look more like these numbers. So you're kind of almost, you can imagine how, and that's a you know, a commonly used number, and that kind of infinitely gets, because it's like the square root of, which is why it's so big. So that gets pretty big pretty quick, and you can see why it's so intensive to try and calculate that. But with quantum, it begins to say, well, actually, these types of unsolvable problems are becoming within the purview of what has never been possible. And you can see here there's Moore's law, and this is an IBM researcher who famously claims back in the I forget which, it was sometime in the 1900s, that compute was going to essentially double every 1.5 years. And there's a scale of limited return. So with classical computing, that it was kind of hitting a ceiling where we've kind of got to the nth degree of like the optimizations and things like that. There's only so much higher we can go. But the introduction of quantum computing actually brings, the continuation of that scale, which is actually pretty scary when you're continuing to add more and more and more compute, and a different type of compute that's optimized. It actually brings a very real risk to cryptography. This is a study that was done. It was a study where a number of quantum and cryptographic experts were interviewed, and they answered based on how likely are we to see quantum-based threats within the next 5, 10, 15, and so on years. And I'm assuming this is like a percentage of those people. So kind of about 5% of people for in the next 5 years, and that kind of dramatically increases. And this is still people who think, experts who actually think, we could well see something in our lifetime, and that actually gets more and more to a certain place where it becomes commonplace. So we're well beyond thinking, should we actually do something? And many businesses are still kind of floundering because they don't really know, like trying to migrate your cryptographic algorithms is a very big task. And trying to even understand what assets you have is a struggle. And it's something they've been putting off for a long time, until really a number of organizations like the NSA and NIST and NCSC in the UK have started creating guidance that we really need to be doing something a lot sooner. And there's a lot of mandates on certain companies, including on Microsoft, to deliver on that as well. There was also a recent, I say this is recent, there was an announcement on OpenSSL and other providers who are committed to supporting the adoption of this. And for those of you who don't know, OpenSSL is what the majority of open source applications use to update their algorithms. So big providers like this, again, make it more possible to migrate, and they're giving the building blocks to migrate across, which is obviously good to see. And as Microsoft, we find ourselves as a bit of a unique stakeholder in this mix. So we are both the creators of quantum, we are the managers of large infrastructure that we're providing as service providers, and of massive amounts of people. So we employ over 200,000 employees ourselves. So we're also defending ourselves, and we're also a security provider. So we are also thinking about securing ourselves. So our role is quite unique, and the types of ways that we're thinking about this problem is just way different to, say, IBM, they're less caring about having to set up, say, a quantum computing algorithm tool, for example. And many of you may have noted the announcements, which we do talk about on our docs page, which is the Encrypt library. And just to talk about what that is, so that's our primary library, and that has all types of algorithms in it, including quantum resistant ones. And that's what we really use to integrate with our ecosystem. So whether it's Windows or our various platforms, that is really what's referenced to maintain and to source and to kind of contain and look after all of the algorithms that are in there. The way that the algorithms are organized means that we can achieve compliance with various regulations as well, which is like the FIPS regulations and other ones as well. It's optimized for performance, and it's really to help provide that initial phase of providing that quantum safe transition for algorithms as well, which is really key. It allows customers and even us to begin to think about how we migrating our own custom applications that aren't relying on, say, Windows ecosystems, etc. There's another concept as well. I tried to find a good graphic for this, but I couldn't quite find a good one. But there's a common trend recently, which is called a hybrid model of doing essentially encryption. So one of the biggest challenges that many customers will have is legacy tech. So that's kind of low power IoT powered tech. or other types of technology. And the challenge there is they're not going to be able to handle or run the newer or even support the newer cryptographic algorithms. So, and actually the whole notion and the idea of quantum cryptography is actually quite new. And we all know that the academic realm exists because we know that the professionals make errors and mistakes, and what we often collectively think is true sometimes may just be proved wrong in an instant in one paper. So we've got all of this history of traditional cryptography, and the general idea is we have both the use of a cryptographic algorithm as well as a traditional algorithm. So you kind of get the benefits of the performance and the longevity and kind of falling back in case one of those gets compromised. And there's kind of various Kyber related algorithms, hybrid algorithms that are becoming quite popular nowadays because of that reason. And I expect this is probably going to be quite a popular way forward for that kind of compatibility, for the longevity issues that I've just outlined. So I'm kind of expecting to see that become more prominent as well. In terms of, and I'm getting now into kind of what our response is and where we're going as well as Microsoft and the quantum safe team. So our principles is always that we want to remain committed to ensuring our platform and services remain secure, that our supply chain is secure, that every customer and partner is secure, that they're enabled to be secure, that we've established that accountability that we've kind of seen earlier, as well. We've integrated various standards into how we think, and our various frameworks, and we've already done the discovery phase and the figuring out what assets we have, the roadmap to how do we remediate and how do we get to green on becoming quantum safe by the dates that I'll share. Obviously, I won't kind of share specific dates in terms of what we're committing to, and there's a lot of reasons to why we can't do that yet, but I can kind of give you some rough estimates, and then also raising awareness that this is important, and that's becoming increasingly my role. I was briefing the UK government recently just to create the urgency and awareness around, why this is important, why we need to start those conversations now, and we need to get on top of it now, because it's one of those things that once it gets on top of us, and once it starts getting exploited, it becomes very difficult to claw back from. We're also thinking about how we transition our first and third party connectors, and we've got a bit of a model of tiering of how we're beginning to think about how we migrate, and we're also producing guidance on how we're advising customers would consider and what steps can they be doing to migrate and to mitigate some of this already, and obviously looking to new solutions all the time as well. The CNCSA is the NSA's timeline that they're holding various organizations accountable to. So this is a US timeline, and that we're targeting 2033. The UK is a little bit more conservative in that, or probably liberal, depending on which way you see it. They're targeting 2035, which is based on the NCSC's guidelines. But I think really the call is that we need to be thinking about that now. And there's various stages, like thinking about how the software and firmware signing and the various web browsing, various kind of different equipments, and there's some guidance on what targets should be, and aspirational targets. And you've got the little kind of the stripe line here, which is where it's an option to be used. And again, I think we're going to align loosely to that, where that's going to be there, and then it's going to be on by default, and preferred by that point here, which is our standard on by default security default approach, that we see in other areas kind of going forwards, with kind of phasing that out from here onwards. Managing the quantum threat is no different from any security threat that you have to manage, and you can manage that effectively with risk and with a good framework, as I so love to do. And the first step is always the discovery and the creation of an inventory. And so that's figuring out what do I do and having a clear plan for, and that's, shortly followed by establishing accountability. So owners and enriching that data, categorizing and labeling that data. So you get a lot more useful insight out of that. And then providing a useful risk model, again, to calculate the various risks. The most risk areas are going to likely want to be done first, or your highly critical assets, for example. Also, defining in the next phase, a strategy, the right buy-in from leadership for funds, defining what the right outcomes are, plotting, or like a Gantt chart, or mapping out what are the required steps to achieving that change and the core metrics in phase 5. What a good influenceable leading metrics, and there's a good distinction between leading metrics and what I would call lagging metrics. So leading metrics are things that you can influence, such as defining a good, like focusing on a very specific item. That is, if all you do is focus on that item, it's going to move the needle in helping you become more secure and helping you achieve your objectives, rather than a good lagging measure is we got quantum safe, or we got 50% there, and that's not really influenceable. And that's a big organizational challenge that applies to many different areas. And then lastly, reporting and implementing and configuring tooling and continuously learning from that implementation as well. Which leads us on to cryptography posture management, which is a defender tool, and that's at least the plan at the moment. Who knows where the platform-based approach is going to go, but that's going to be a discovery tool. And that's going to be the primary tool that customers, and it's really the only tool really, and there's a few other minor players on the market at the moment, but there's not really a tool that helps you discover what cryptographic algorithms exist. And not only that, but it's going to help you manage and remediate those vulnerabilities and gaps. And I'm hoping that really it's going to provide that evergreen, the days of having to migrate your algorithms and that mammoth task of doing that's going to be over, and actually customers are always going to be on the evergreen, on the latest, the most secure algorithm, because then it's baked in and it's automated. Is going to be, I think, the goal there. And then it's going to have GitHub integrations as well, so it's going to manage cryptography that's done via code, or various things that you're integrating into different areas that are kind of DevOpsy. But I wanted to share just a couple of screenshots around the how this tool is going to look like. So this is the tool in existence at the moment. As you can see, it's a Defender driven tool, and it's going to exist under the asset section, and it's going to have its nice little cryptographic section as well. And you can see all the assets here. It's going to give you kind of the total amounts, and obviously it's kind of basic in its form at the moment, but it lists out all of your assets. It organizes it by a ranking of how important is this, and it's going to show critical at the top, and it's going to allow various filtering to be done, and it's going to allow you to break out, show me just keys, show me my cryptographic libraries, hash functions, which are essentially like when you hash something, you kind of run it through, like we call it like MD5 or SHA-1, and it creates a ciphered, or like a ciphertext, which is like it kind of creates like a signature of that, and then the various protocols that are used. And you can kind of see here, you can kind of click into the various artifacts, and you can kind of map those out, view various relationships of those algorithms, summarize. And I'm really hoping that we can get to a point, especially with the platform-based approach that's coming, which I think will be announced at Build, from my understanding, is that's going to bring native better integration of reporting into Defender. So that's going to solve the reporting challenge and having to store that data. It's going to give you a good level of retention to store all of that information.
I hope you found that video very useful. Please let us know what you'd like us to cover in the future. We'll see you again soon.